Okay, so in this video, we're going to revisit conservation energy. And what we're going to do is we're going to add in, again, that rotational aspect. A lot of these videos in this unit will talk about the linear relationship to the rotational side. And that's what we're going to do here. So when objects rotate, because they are moving, they're going to have kinetic energy, but we're going to call this rotational kinetic energy. Sorry, turn the pen on. So again, we're going to call this rotational kinetic energy. And the reason why we're doing that is because it is rotating and moving. Okay. So what we called way back in unit 4 kinetic energy, or what we call regular kinetic energy, that linear kinetic energy, we're now going to give that the special name of translational kinetic energy. And it's going to be K sub T. Now, it is the kinetic energy of an object that moves from one point to another, or with some velocity, or we can use the equation K equals 1/2 mv squared, right? That's just our regular kinetic energy of mass time, 1/2 mass times speed squared. Again, to remember that that kinetic energy, or all energy, is a scalar quantity. Now, rotationally, it's going to be the kinetic energy of an object that rotates from one point to another. So again, here's your difference. Moves means linear, and right there is that rotates, right? And so again, if we take that rotational, or the linear equivalence of rotation, and we kind of manipulate the formula, you're going to see that the equation is going to be K equals 1/2 I omega squared, right? Remember, I is the moment of inertia. That is the rotational equivalence of mass. And omega is angular speed, which is the rotational equivalent of speed, v. Okay, so what really happens is that we change up our energy equation, right? So the statement of conservation of energy for rotating objects now just simply becomes E equals UG plus US plus KT. So that's the stuff from unit 4, right? Or excuse me, unit 3, 4, sorry. Now we add in that rotational aspect, right? And this is going to equal a constant, okay? And so here's just some example problems, right? So again, right, you can run in conservation energy, so you can have like now an object rolling down an incline, and if you know what the object is, if it's a hoop, a cylinder, a disc, right? If it's a sphere, a hollow sphere, a solid sphere, you can figure out the rotational kinetic energy. Um, the one thing is, you may have this V equals R omega becomes a very important relationship, because here's your connection between the two. So if you have a V, you can substitute in for omega. If you have an omega, you can substitute in V, and so forth. But here are just some example problems. It says calculate the rotational kinetic energy of the Earth due to the rotation about its axis. Assume the Earth is a uniform sphere with a mass of 5.98 times 10 to the 24th kilograms and a radius of 6.37 times 10 to the 6th meters, right? And so we're talking about, here's our Earth. It's going to rotate about its axis, and we're trying to figure out what is that rotational kinetic energy. So the first thing we have to do is find the rotational speed, right? And so it takes Earth, essentially it does 1 revolution per day. And so we're going to do kind of a dimensional analysis, or a factor label method here. So 2 pi radians is 1 revolution. So there we are now in radians, because we got to get this into radians per second. 1 day is 24 hours, right? Let's see, 1 hour is 60 minutes, right? And 1 minute is 60 seconds, or you can do 1 hour, 3,600 seconds. And so that gives us a rotational velocity or speed of 7.27 times 10 to the negative fifth radians per second. Okay, now we need to find the moment of inertia of Earth. And I apologize for, so it's going to be I equals, for a solid sphere, it's 2/5 mr squared. And so it's going to be 2/5 of 5.98 times 10 to the 24th times 6.37 times 10 to the sixth squared. And so this is going to be a pretty big number, which is 9.71 times 10 to the 37th. And now you got to be careful, the unit's going to be kilograms times meters squared. Okay, and now we can plug it into our equation. So K is equal to 1/2 I omega squared. So 1/2 times that big number we just found. Again, you don't have to write the unit. I know sometimes I write the units and sometimes I don't. Times 7.27 times 10 to the negative fifth squared. And so our energy, our kinetic rotational energy is going to be 2.94 times 10 to the 29th joules, right? And so, as you expect, Earth has a big I value, but it does have a small K or omega value. Um, but what that translates into a big energy. Okay, and so the next example we're going to look at, it says a thin walled spherical shell rolls on a surface. What fraction of its total kinetic energy is in the form of rotational kinetic energy about its center of mass? And so the way you think about its total kinetic energy, right? It's 1/2 mv squared plus 1/2 I omega squared. Okay, and we know its rotational energy is 1/2 I omega squared. And so something that we do need to do here is get this all into i's and omegas, right? And so we have that we need to turn into an omega in some way, and then we have this that we need to turn into um, a sorry. We want to get, so we're going to turn that the v into an omega, and we're going to turn that into a mass. Okay, so we'll do the same thing here. We'll turn this into a mass. So we're going to get these all in terms of omega and all in terms of mass, right? And so for a hollow sphere, it's going to be 2/3 mr squared, and we know omega is going to be v over r from this right here. Okay, and so I'm going to substitute all this in. So I'm going to get 1/2 m. Um, sorry, yes. So I apologize. We want this in terms of omega. So this is going to be r omega plus 1/2 times 2/3 mr squared, and we're going to have omega squared hanging out here, and this will be 1/2 times 2/3 mr squared omega squared. Okay, so this is a lot. This problem here is going to be a fair amount of algebra. Okay, and so the top part ends up being 1/2 mr squared omega squared plus, um, this ends up being 1/3 mr squared omega squared, right? Divided by, and this ends up being 1/3, right? Mr squared omega squared. So you can see, really, we're just looking at the fractions because all this mr squared omega squared is going to cancel out. And so we're going to do 1/2 plus 1/3 over 1/3. And so this is, let's see, it's going to be 3/6 plus 2/6 over 1/3. So it's 5/6 over 1/3, right? And if we do our 5/6 times 3/1, do I have that backwards? Oh, I have it backwards. Sorry, I apologize. These should be flipped because we're looking for um, rotational energy to its rotational kinetic energy to its total kinetic energy. So I have those two flipped. So I apologize. And so it's gonna be 1/3 over 1/2 plus 1/3. So here these two would flip. So it's gonna be 1/3 over 3/6 plus 2/6, which is 1/3 over 5/6, which becomes 1/3 times 6/5. So that becomes one, that becomes a two. So 2/5 of its kinetic energy is rotational kinetic energy. Okay. So in the next video, we're going to shift from energy to angular momentum. Again, still making that connection between linear and rotational.